Hi all, I wanted to take a minute and go through the mechanical lung project and give you some hints on how to get started with this. So if I were doing this, and let's see, I'm going to make up some of my own C and R values. So let's suppose that my lung compliance is going to be 0. Let's see, let's go 0.2 liters per centimeters of water pressure. And I'm going to let my resistance be 4 centimeters of water pressure. H2O for water. And I'm going to go through this exercise as if those were my C and my R. Okay. So I've read through this twice, which is what I would suggest you doing. And then we're going to start to answer questions. So we're going to start here. So find the time for inspiration, TI, expiration, TE, and total breath time, T total. Okay. So I'm going to go back to the words and see if I can figure out where they describe that. So keep in mind that TI is the time it takes for you to fill up your lungs. So from the beginning of your breath to when your lungs are full. It says, first we calculate the length of inspiration, expiration, and the total breath. Hey, this is an indicator that this is what I want. The length of time of inspiration is based on the resistance and the compliance of the lungs. We first find a time constant TS. So here's something I need. By multiplying the resistance and compliance. So the first thing I'm going to do down here. So number 1, I need to find my TS, and it says by multiplying my resistance and compliance. So just a reminder, my compliance without the units is 0.2, and my resistance was 4. So my TS would be C times R, which is 0.2 times 4, or 0.8, and that's going to be in seconds, right? If you think about the units there, it's in seconds. Then, what does it say next? Next, it says, from empirical data, studies have found that in 5 time steps, the lungs will inflate to 98% of the total volume. For our calculations, we'll use this value as the time to fully inflate the lungs. So the time to fully inflate the lungs is your TI, and it's 5 time steps, okay? So for TI, it's 5 time steps, my TS. So I'm going to take my TS and I'm going to multiply it by 5. So 0.8 times 5 gives me 4 seconds to inhale. Not bad. If you think about breathing in for 4 seconds, that's reasonable for a TI. Okay, TI. Next, we want TE. Let's go back up and see what it says. Then we consider a ratio of inspiration to expiration. For this example, we'll use a 1 to 5.6 ratio of inspiration time to expiration time. Okay. So what they want us to do is they want us to use a ratio of 1 to 5.6 as our ratio of inspiratory time to expiratory time. Okay. That's what it means to be proportional in using that as a ratio. If we cross multiply here, this is that TE equals 5.6 times TI. So to get my TE, I'm going to take 5.6 times TI. So let's 5.6 times my 4 seconds. And that's going to give you 22.4 seconds. It's a long breath. And then your T total is just inhalation plus exhalation. So that's TI plus TE. And that's going to give me 26, not 64, but 26.4 seconds. Okay, and those are the first 3 things that I'm being asked to find. That's all in number 1. Perfect. Number 2. Number 1, check. Number 2, if PEX is equal to this, then calculate PEX. Okay, so this is, PEX stands for an escaping pressure. So our system is not perfect, and that means that some things are going to escape through leaks in the airway or whatever. So the PEX is defined as PAP times E to the TI over R times C, and E to the T total over R times C, and I believe they're both minus 1. Let's go back up and check. Yep, both minus 1. And these are all known quantities. So your PAP is 10, Then you have E. Ti is, let's see, 4. So 4 over your R times C. And R times C was my actually TS, so that's 0.8. So 4 over 0.8 minus 1 all over. My T total was 22.4 over the 0.8 minus 1. Okay, now make sure that you put this into your system correctly. I'll show you how I do it on Wolfram Alpha. But before we do that, let's simplify it. So 4 over 0.8 is 5. So this is e to the 5 minus 1. And 22.4 divided by 0.8 is 20. Hold on. I think I did that wrong. Yes, I put in the wrong number. Make sure you put in the right number. This should be 26.4. Because it's my T total. If you take 26.4 divided by 0.8, that's 33. E to the 33 minus 1. Okay, let's go ahead and put that into Wolfram Alpha. So we want 10 times the quantity E, and I'm going to use the EXP because I think that's easier to type. And I want 5, e to the 5, and then minus 1, close my parentheses, divided by EXP of 33, minus 1, close my parenthesis, and hit enter. And we get this big number right here. Whoa, where'd it go? There it is. 6.87 times 10 to the negative 12th. And that's my, my escaping pressure, my PEX. So that's my answer to part number 2. Oh, sorry. Now, when we go on to number 3. So 2, check. Number 3, the volume of the lungs at any time during the inspiration is given by this big formula. And all we have to do here is plug in our PAP, our PEX, and our RC. So we have, let's see if we can memorize this to put it down here. Number 3. VI. So this is the volume of in the lungs during inhalation. That's 1,000. And 1,000 just lets us convert between the units for this R and C are in liters. But the test lung that we're going to talk about is in milliliters. So in order to convert liters to milliliters, we've got to multiply by 1,000. Okay. Let's see what this is again. C times PAP minus PEX. So times C times PAP minus PEX times 1 minus, I believe it is, e to the negative 1 over RCT. Okay, so we need to plug some things in here. 1,000 times, my compliance was 0.2. So right away, this is going to be 200 times 10 minus PEX is the 6.87 times 10 to the negative 12. And then you have 1 minus E to the negative 1 over 0.8 was my RC times T. All right, clean that up. 6.87 times 10 to the negative 12. And we're going to have 1 minus, so 1 over 0.8 is 1.25. Or in fractions, 5/4. So negative 5. Oh, where's my E? So negative 5/4 T. Then we want the VE, which is going to be similar, but slightly different because there's no PAP. Remember, we talked about the fact that when you exhale, there is no applied pressure at the airway. So there shouldn't be a PAP here. And so you can see the difference. You've got 1,000 times C times PEX, and then the E term minus 1. So our VE is 1,000 times C times PEX times e to the t total minus ti times 1 over RCT. Nope, that's not right. Let's check it again. 1 over RC, t total minus t. Was close. Let's fix it. 1 over RC, t total minus t. And then a minus 1 over here. Okay. Underneath that one, my VE will turn out to be 1,000 times 0.2 times 6.87 times 10 to the negative 12 times e to the 1 over RC we said above was 5 over 4. My t total was 26.4 minus t minus 1. And you can simplify a little bit if you like. This again is the 200 times the 6.87 times 10 to the negative 12 times e to the 5/4. 26.4 minus t minus 1. And let's see, if we multiply that by 2, so 6.87 times 2 gives me 13.74. Times 10, I was at negative 12, but now multiplying by 100 was times 10 to the 2, so that's negative 10. And e to the 5/4, 26.4 minus t minus 1. Okay. And that's where I'm going to stop because we're going to work from here. We've got our VE and our VI. And really what we want to do next is we want to jump into the next piece. So what we're going to do in the lab is we're going to do part number 5, which is graph the piecewise function for the volume. So we're going to graph VI from 0 to, in my case, 4. And then we're going to graph VE from 4 to 26.4. Okay. And then think about some things I want you to think about. What are some things that you're assuming about each breath? For example, what's the volume at the start, the middle, and end of each breath? And then we're going to be jumping into part B. Okay, now that you have these graphs established and you know what's going on, we want to talk about two things. We want to talk about the volume, which we have, the flow, and the pressure. So pressure is just 1 over C times the volume. So this is a scalar multiple of the volume. So you're just going to take your volume and you're going to divide it by C, right? Notice that both of those VI and VE both had a C in front. And so you're just going to take that out, right? So eventually you're going to divide everything by 0.2. So the answer to number 8 is relatively straightforward. Number 7, the flow rate is the rate of change of the volume in and out of the lungs. So anytime we see rate of change, we should be thinking derivative. So if I want to find the flow, I want to take the volume and take the derivative of the function. Now this might be a little tricky. So this is number 7. So let's take a look at it real quick. We'll write down 7 and 8 and then we'll call it a day. Okay, if I'm looking at VI is this one. And I want to take the derivative, okay? Notice everything that is sitting out front here are just numbers that are being multiplied together. So when I find my Fi, which is Vi prime, I'm just going to keep those numbers out front, right? If it were a 2 out front, we would just put down the 2. So we're just going to keep that out front. So we're going to have 200 times 10 minus 6.87 times 10 to the negative 12. Okay, then we've got the function part, which comes next. I have 1 minus e to the negative 5/4 t, okay? The derivative of 1, 0, I don't need it. Now I have the negative e to the negative 5/4 t. Okay, remember that this is a chain rule. So I'm going to write it down here. So we're working with we have negative e to the negative 5/4 t. So my parentheses go here. The e is on the outside. So the derivative of e to the anything is e to that anything. So I'm going to keep my minus. The derivative of e to the negative 5/4 t is e to the negative 5/4 t. But chain rule says then you've got to multiply by the derivative of what's inside. So I'm going to have to multiply here by negative 5/4. Okay, and those two negatives are going to cancel out for me. So this is going to be 200 10 minus 6.87 times 10 to the negative 12. And then I'm going to have positive 5/4 e to the negative 5/4 t. And that's my VI. That's my first part of the flow. We've got to then do the same thing with my expiration. So we've got to take VE and take its derivative. Well, VE is right here. So again, we have this number sitting out front. So you have a number out front. We're going to take that with us. So the derivative is going to be 13.74 times 10 to the negative 10. Then we've got our function piece inside. Now this negative 1 over here, just a number, its derivative is going to be 0. So the only piece that I have to worry about is this one. Okay? And again, with exponentials, the e is on the outside and that exponent is on the inside. So when we take our derivative, we need chain rule. The derivative of the outside is the e to whatever's there. So I get all that back again. And then I multiply by the derivative of what's inside. And what's inside there, now be careful here because really, let me write this one out. What you have really here is e to the 5/4. And if you distribute that, you get 26.4 times 5/4. Comes out to be 33. We've seen that number before. So 33 minus 5/4t. So when you look at the derivative of the inside of that, the 33 doesn't have a derivative, and negative 5/4 t gives you negative 5/4. So you get, let's see, 13.74 times 5/4 gives me 17.175 times 10 to the negative 10. With a negative out front, e to all of this stuff. And if you keep it distributed, you can get 33 minus 5/4t. And that's my derivative for the expiration. So I have two pieces to my flow, the inspiratory flow and the expiratory flow. Okay. And then to get the two pieces of your pressure, as I mentioned before, you're just going to divide each one by 0.2. So essentially your 200 out here will become 1,000, and this will change as well for the VE, your PE. Okay, so I'll let you guys try to write that one out. So see what you can do with this, and we'll meet on Monday in the computer lab. We're going to be in TEGC 110A. And we'll go over how we put this in Mathematica and get graphs and all that kind of stuff.